darn it. Propane, sorry, losing my mind. And we're gonna have chlorine, we're gonna add a chlorine on here, right? So this chlorine's gonna split apart first, I'm not gonna draw out the mechanism, right? This is gonna split apart. The UV radiation causes to split apart, creating a free radical. Then you're gonna have a proton abstraction, right? And we're gonna form a free radical out of this thing. Now, I have three places I can form a free radical, right? Which one's gonna be the most stable? If you form a free radical here, or here it's primary. You form a free radical there, it's secondary. So by that alone, you should know that your primary region, the main place you're gonna put the chlorine is right here on this secondary one. And that's true, and that's where it's gonna go. Plus, you're gonna get some on the end, right? On either end, you flip it over, so it doesn't matter which end, it'll be the same. And the numbers for this are actually approximately 60% and approximately 30%. Oh, sorry, 40%, what am I saying? Okay? Again, because the secondary is gonna form the most stable free radical, right? And I wanted to put these side by side, and that's not gonna work. Ah, damn it. All right, I guess, right, that's fine. Sorry, I had a plan here, but my plan's going out the window. Again, because I don't have enough board space. Let's take a look at bromine here real quick, and then I'll have to come back. Let's do this with bromine. You're probably thinking we're gonna get pretty much the same result. Which wouldn't be a bad guess, but actually you don't. You get the vast majority of the bromine goes on to the secondary carbon, while only 3% goes on to the primary. So the bromine is more regioselective, right? I guess you can memorize that. Bromine is more regioselective than the chlorine, right? For the major product, yeah. Now, why would this be? Well, we have to take a look at the energy diagram to determine why this is. That's why I want to draw these two side by side, which I could not, but I'm gonna have to erase this. So bromination is more regioselective than chlorination. To know why, we have to, again, we have to look at the potential energy. So here I'm gonna have, we're gonna look at the hydrogen abstraction. In the chlorination, okay? And we're going to look at hydrogen abstraction. For bromination. So here we have our energetic diagram. Okay, we're just looking at the hydrogen abstraction part. With the hydrogen abstraction part, what's going on? That's where we're forming the alkane, we're changing it into a free radical, is what's happening. So we have potential energy here. So for chlorination, we're going to start up here. Now remember, this one had a bigger delta H, right? Here's our EA. Here we're going to have our alkane plus our chlorine radical, okay? That'll take the hydrogen off. This one is going to be, whoops, ooh, I drew that wrong. Actually, no, I'll leave that one. That one will be the third degree radical. Assuming we can have a tertiary one. That would be second. And that would be a first. So primary, secondary, tertiary, right? Again, for all these, this is EA. But look here at this part. They're not that different, right? The EA is not that different. That's why this is less regioselective, okay? That's why the chlorination is less regioselective. The distance between the activation energies is pretty small, so it's not as regioselective. As bromination, if we compare it to that, all right? Let's take a look at the bromination. Okay. For our bromination, actually, the hydrogen abstraction step, it is endothermic, okay? It's endothermic is what we end up with. So we're gonna have our alkane plus our Br radical, right? 'Cause you're getting extracted a proton. And we end up with something like this. That's going to be forming a tertiary radical. Secondary radical, and I didn't leave myself enough room. Or primary radical. Now, assuming these are on the same scale, which they're supposed to be, okay, I'm trying to draw them that way, look at here. Large difference in the activation energy. Thus, bromination is more regioselective, because this energy is quite a bit less than that energy. These energies are much closer together, okay? That's why this is regioselective. Larger difference in EA means it's regioselective. In the case of chlorine and bromine, all right? Hopefully explain all that so it makes sense. Let's take a look at one more example. We'll take a look at an example with a tertiary radical. So we'll take 2-methylpropane, right there, right? There's a hydrogen off there, right? So you can form a tertiary radical. And then we can either do chlorination or we can do bromination. Again, you should already be able to guess what's going to happen. With the Br, we're going to get almost 100% of one product. We get almost 100% of 2 bromo, 2 methyl propane. 100% practically. Okay? This one we're going to get 2 different things basically. The more prevalent here, right, tertiary is the more stable, so that'll be the major product. But then there's 3 other areas to put the chlorine on. So this one turns out to be about 65%. Plus we'd end up with 35%. Remember, if you put it here, here, or here, that all make that one product, okay? That's all the same thing, all right? But, so there we go. All right, again, bromine is more regioselective. Let's take a look at the example problem real quick. Say we have this here. What am I doing? So we're going to do bromination. Now, I'm not going to draw all the products, right? But let's pick these spots and rate them where we're gonna get bromination, okay? Where we're gonna have bromination, where we could have it. Well, so, first of all, let's look here, right? Here, this is gonna be tertiary, okay? So we could add a bromine there. Wherever you're gonna have a hydrogen, right, you could possibly add a bromine, right? You can't there, okay? But you could here, could there, and there. Those are all primaries, all right? We'll come to those in a second. So this is the only tertiary spot. What about the hydrogens off of here, right? This would be the vinylic position. What happened? We did not do that. We didn't take a hydrogen from a double bond, okay? So you're not gonna get nothing there. But you put a bromine there, and here, right? This is the only tertiary, so that'd be number 1. This is secondary, so that'd be number 2. And then all the rest of these are primary, so that'd be the 3rd most likely spot. And if you actually did this reaction, you'd probably end up with about 100% there, or 99%, and then 1% there. But anyway, I'm just showing you all the different spots where you could get your bromination. I'll just draw the major product. Shown there. That would be the major product, okay? What would we have? What would that be? That'd be a chiral center, right? You'd have a chiral center. And actually, you'd end up with both enantiomers. We're gonna see that halogenation, radical halogenation reactions are not stereospecific. That's coming up the next part. But anyway, all right, I hope that's all understandable. Now let's go on to stereospecificity, which there is none, okay? Basically, if you do halogenation, you're gonna end up with a racemic mixture. If you replace the hydrogen on a chiral center, you'll end up with a racemic mixture. If you're creating a chiral center, you'll end up with a racemic mixture. Let's take a look at an example. Long story short though, halogenation, radical halogenation is not stereospecific. That's long story short. Is not stereospecific. Now we're only going to consider, well, I guess I'll draw all 3, okay? So here we have primary, secondary, primary, right? But if you do here, right, that'd be the same as doing it there if you flipped it around or whatever. So basically, what are we gonna end up with? We're gonna end up with 3 products, right? If you do it on an end, it won't be an enantiomer, it won't be chiral. If we do it here, we're gonna have the chiral compound. So we're gonna end up with this. Right, so we end up with 3 products, okay? Again, it's not stereospecific. And again, if you add it here, you can flip it around and be one of those 2, all right? So what do we get? A racemic mixture, right? With those 2. What do we usually want to avoid? We usually want to avoid racemic mixtures. Racemic mixtures are hard to purify, usually. Now I know you have a burning question in your mind. Why is that? Why is that, Cliff? I know you're asking it. Remember when we started out, we drew that the radical, you could either be sp2 hybridized or picture it as or sp3 interconverting, okay? I'm not going to draw one of them, right? I'm going to draw the sp2 hybridization. Remember, we can look at it either way. And why did I not give myself enough room? This will be the sp2 hybridization, right? We had this unhybridized p orbital in sp2, right? This is an unhybridized p orbital. So you can see the chlorine, right? We can have one electron in here. The chlorine can come from either way. And you get your racemic mixture, right? You can also draw the sp3 one, right? But whatever, it's basically the same thing. And the same story applies to bromine, okay? Same story applies to bromine. However, bromine is more regioselective, right? Let's take a look at bromine. Why do they draw such a long mouth? I guess I could have shortened it. Let's do that, okay? Again, I told you this is not stereospecific. So with this thing, right, regioselectivity, where are you going to lose your hydrogen from? There. Since it's bromine, it's more regioselective. So basically you're going to get one product. See, we're going to draw the major product. Now here we already have a chiral center, right? But once I lose that proton, it doesn't matter. I can come from either side. Thus, I'm going to once again get a racemic mixture. And I'm going to end up with this. Again, a racemic mixture. Okay? Pretty straightforward. Let's do one more real quick. Well, hopefully you got the picture down. Yeah, that's terrible. It's all right though. All right. So where are you going to get bromination occurring, right? There's two spots where you're going to form